watched before. No? Okay.
Sometimes you press control and...
Okay, so... How to, like,
So I have to might need to download the actual PowerPoint. Or copy and paste it.
Okay, the video.
Oh, nothing you do bad.
Back to the first, which then sails off towards infinity. 3 total plaques. What about if the first block was 100 times the mass of the second one? I promise I will explain to you all the relevant physics in due course. It's not entirely obvious how you would predict the dynamics here, but in the spirit of getting to the punchline, let's watch what happens. The second one will keep bouncing back and forth between the ball and the first block 100 times its mass, like a satisfying game of breakout, slowly and discreetly redirecting that first block's momentum to point in the opposite direction. In total, there will be 31 collisions before each block is sliding off towards infinity, never to be touched again. What if the first block was 10,000 times the mass of the second one? In that case, there would be quite a few more clacks, all happening very rapidly at one point, adding up in all to 313 total collisions. Well, actually, hang on. Wait for it. Wait for it. Okay, 314 plaques. If the first block was 1 million times the mass of the other, then again, with all of our crazy idealistic conditions, almost all of the clacks happened in one big burst, this time resulting in a total of 3,141 collisions. Perhaps you see the pattern here, though it's forgivable if you don't, since it defies all expectation. When the mass of that first block is some power of 100 times the mass of the second, the total number of collisions have the same digits as pi.
Yeah, so that's my topic today. We're gonna solve this question. Okay, so firstly, it is a perfectly idealized model. So Annie, give me an example. Why? Yeah, no
friction.
what? No frictions, right? And no what?
No loss end.
Yeah, so you get right.
Did you warn you about that?
Yeah, and there are 3 things we have. It's because it is purely elastic collision, so the momentum must be conserved, and the kinetic energy must be conserved. Okay, so Sunny, give me 2 equations about momentum and kinetic energy.
The total momentum of the system is m1v1 plus m2v2, and the kinetic energy equals to half m1v1 square plus a half m2v2 square.
Yeah. So we can see here, all the kinetic energy will be a constant, and the momentum that's m1v1 plus m2v2 should be a constant. And here the front block is m1 and the back block is m2. So this is 2 basic equations. Let's resolving it. So firstly, let x be root m1 times v1, and let y be root m2 times v2. And we put it in kinetic energy formula. We can get this one. And anyone know what is this equation stand for? Yeah, a circle. A circle. So we finally get something that related to pi. Let's put it in the axis. So first step, we need to find the first point that when they are all at rest, and we can see the first point is here. It's just before the first collisions, because in the graph here, V2 has a speed with that direction towards the wall, and V1 is 0. So let's like define this as negative. So in the axis, we can the point is on the negative axis of x, negative x-axis. So step 2, we need to use our conservation of momentum. So just resolve it. So let x be so x is root m1 times v1 and y is root m2 times v2. Put it into the equation. We got this one. And m1 and m2 are all constants, so it is an equation stands for a line. And so all of the points that v1 and v2 in on these circles stands for the conservation of kinetic energy, yeah, because we got this circle. And all the v1 and v2 on this line here stands for the conservation of momentum, right? So their intersections satisfy the conservation of momentum and kinetic energy. So we know this point is when after first collisions, the point here will jump to here. And step 3, reflecting about x-axis. That's our second collisions. When m2 gives a speed to m1, and this speed is v1, right? And let this front block collide the wall, and because it is elastic collision, so there is no loss of v1. So v1 is just change the directions to opposite, and the magnitude of its speed of m1 doesn't change. So on the axis, the point jump from here to here because the magnitude doesn't change and the direction change to positive. And next collision is just repeat. It corresponds to a jump along a line with gradient minus root m1 over m2. So this line has the same gradient with this line, and yeah, so we can get the third point and so on. So let's fill in the rest. So it looks like this, and there is an end zone. It's here. The green one, do you see that? So, yeah, so this is the end zone. This area means the point in there just like its end here. So it's this is when V1, V2 greater than V1. Because let's back to the graph here. when the speed of m2, when the velocity of m2 is greater than velocity of m1, they can't collide. So when the graph, when the point enter this end zone, so they can't collide anymore. Yeah, so the end zone is V1 smaller than V2. And you probably noticed all the arcs on the graph have same length. It's just you can see it. It's yeah. And why is it? We need to use inscribed angle theorem. So the angle here is theta, and so the angle here is 2 theta because it's the center. So we can see the arcs here is 2 theta in radians. So all the arcs between the collision points are same. So yeah, so we can work out the n, such as we plus all the arcs together, and it must be smaller than 2 pi because yeah, 2 pi is this circle. So the n would be the same as the number of collisions between blocks. Yeah. So we can add all the 2 theta together, and we can get this equation is n theta must be smaller than pi. And let's just put theta equals to 0.01 into this equation, and the n be let n be 3.14. And so it can get the pi. So the first 3 digits of pi. Yeah. And that's the relationship between the collisions and the pi. Thank you.